Okay, so we drew an equilateral triangle, and I showed you that equilateral triangles have a very interesting property. If you pick a point inside the triangle and drop the perpendiculars from that point, we find that the sum of those three perpendiculars is what?
It's the height of the triangle.
Incredibly, the sum of those three perpendiculars doesn't change any point inside the triangle. Do you remember how we proved that?
Well, because we said they were separate lengths,
Yep, they're separate lengths.
and in the middle point they were all the same.
In the middle point they were all the same, yeah.
And then when you're moving it around, some of them decrease by a certain amount, some of them increase by that amount.
Yeah, that's true.
So that's their sums. That's why their sum stays consistent.
We actually proved that it was equal to something. Remember what we did?
I don't think so.
Well, we've got these right angles. So what do you think is going to help us?
Right, I think we did right triangle. We used some right triangles.
Okay, how can we make some right triangles in here?
Well, we can do that.
There's two. There's two more. And there's two more. What do we know about those? What can we say about those 6 right triangles?
That there's pairs of them that share hypotenuses.
There's pairs that share hypotenuses. These 6 right triangles have a very special property when you look at them all together.
They add up to the area of the big triangle.
They add up to the area of the big triangle, and their heights happen to be the sums that we're looking for. So when you calculate these areas, you find that the heights, because the areas add up to the area of the big triangle, the heights add up to the height of the original triangle. But that's enough detail on this. So what we did, getting back to our problem, is just, so let's pretend we have an equilateral triangle whose height is 1. And that means all the heights are going to be 1, right?
Yeah.
And now what we're going to do, unfortunately I didn't draw it quite right, we're going to take all the points where the height going this way is less than a half, the height going this way is less than a half, and the height going this way is less than a half. That's a better drawing of it. Sorry for the two confusing drawings. Okay. And here's my triangle. And in here, I have the 3 heights are all less than a half. I know anywhere in here the heights add up to 1.
Yeah.
And the only question is, do these form a triangle in here? If I pick something, if A is less than a half, A is between 0 and less than a half, 0 is less than B is less than a half, and 0 is less than C is less than a half. In other words, something inside here. Do I know, for example, that A plus B has to be greater than C? Do I get the triangle inequality? And once I prove A plus B is greater than C, this is all symmetric, so it'll prove everything else. So how can I prove that A plus B is greater than C?
Well, A plus B
So here's the height A, here's the height B, and here's the height C.
Well, I know that A plus B is C minus 1. I mean 1 minus C. Because it's the entire height minus the C part.
Okay. We know that A plus B plus C is 1, so that means A plus B equals 1 minus C. Okay.
So we can substitute this value for A plus B back in here.
Okay.
So we get to 1 minus C is greater than C.
Alright, that's what we're wondering. Is that true?
Then we can add C to both sides.
Okay.
1 is greater than 2C. So C is greater than, 1/2 is greater than C.
Is that true?
Yeah.
And that's true. So we were wondering if this is true. We knew this was true. This plus this would mean this was true. This would mean this was true. Is this? And it is true. So now we can go back up and we find that the triangle inequality holds. And the same exact argument would show that b plus c is greater than a, and the same exact argument would show that c plus a is greater than b. So all three of the triangle inequalities hold, which is what we need. So any point we pick in here, we get a triangle. Any point we pick out here, or out here, or out here, we don't get a triangle.
So it's 1/4.
So the probability is 1/4. It's like throwing a dart at this equilateral triangle and we got to land in this inside equilateral triangle. It's pretty cool, right?
Yep.
That's pretty cool. That's a geometric probability problem, and it shows a very cool application of the triangle inequality. All right, good job this morning, hon.